Hey YouTube, and welcome back to the IoT Developer Masterclass. Up until now, we have discussed how IoT systems can be made smart by applying preset configurations and control over the internet. In this video, we'll be discussing how IoT systems can be combined with machine learning and what benefits it can have on our system. For example, we'll be building an IoT system that can connect to an ML API service or an ML service and with this ML service, it can determine the configuration settings for a particular home. Here's our problem statement. Francis owns a home. It's summer, and Francis understands that Parsons, his dog, will need his room cooled during the daytime on weekdays, especially when Francis is at work. In this exercise, we will design an MLoT system for Francis that can learn from his personal room settings and then make control predictions based off of the control sensors and time settings in his apartment. Now, the idea behind this is that in previous classes, we've learned that systems are smart by making pre-configurations, right? Setting and say, okay, when this temperature is above this, turn the system off or turn the system on, right? Or maybe when you're not at home, you can have your phone or your device or your smart device connect to your device that's at home and change the settings or, of the devices in your home, your smart device. Now, this is going to be a little bit different in the sense that this system is going to learn over time from previous settings. And that is why we're introducing machine learning at this point. We develop an ML model that looks over historical data of past settings. And based off of that, after developing our model, we can then send input of our sensors, right? So we send our sensor settings into the model, and the model gives us a prediction if the fan should be on or off. Now, in the first part of this session, this video MLoT session, we will cover some definitions of IoT and machine learning systems. We will develop a simple ML algorithm that can detect hack defects in patients. In the second and third parts of this video, this MLoT session, we will develop a machine learning algorithm for our problem statement, which is this problem statement here, and host it on our cloud. We would also show I would take you through how you can host it on a Linode server. I really hope this tutorial interests you. I'll try my best to explain and simplify the process as best as I can, and I hope you learn from it. Again, please feel free to subscribe, like, comment, and share these videos. Now let's get into it. From our previous definitions, we defined the Internet of Things as a connected network or chain of things, right? And these things are usually what we call devices that can be monitored, controlled, and can communicate together over a given network. So they can all communicate together, or they can communicate with our smart devices, right? Now, generally, we know these things improve productivity. The IoT improves productivity and saves time, and also helps with pre-programmed automation and control schedules. Now, adding machine learning into this, just a simple definition of machine learning is a type of artificial intelligence that allows software applications used in everyday lives to become more accurate in predicting outcomes without being explicitly programmed to do so. So ML algorithms generally use historical data as input to predict new values or new output, right? So this application of machine learning, right? Machine learning generally also helps improve productivity and save time. And you've seen cases like that with ChatGPT and some of the other ML algorithms that are out there. Some of them generate images, and things like that, right? It also learns automation and schedules from historical data, right? So using machine learning, you can learn all the automation schedules and that has been programmed with the Internet of Things. And once it learns this, it can use that information to do some prediction. Now, in machine learning, you can also analyze large data sets and extract valuable insights and information from these data sets. You can use it to, when you extract that information, the model that you use to generate, that's being generated, can be used to predict future trends and behaviors and outcomes. Now, machine learning also helps with personalized control and content and recommendations. And you'd see that in maybe your YouTube videos or videos that you watch maybe on Facebook. Basically, as you watch these videos, it learns from previous choices of videos that you've done in the past, and based off of that, the recommendations that will come to you for the next video might be something that you are likely to be interested in. Also in Netflix, you might see when it recommends videos to you, it might recommend something that if you like maybe sci-fi movies, it'll probably recommend more sci-fi movies for you to watch. It can be quick and fast when testing and detection from errors. When we talk about ML systems, we talk about an ML model. And sometimes this ML model is called a black box. And that's what is usually used to make an ML system. So generally, you have some algorithms that you use to create a model, and then from that model, you extract that model, and then you use that model for your prediction. So generally, a machine learning model is a mathematical function that can be trained on data to perform a specific task. Now, once the model has been trained, you can just use the model to make the predictions. Essentially, what this means is you have historical data, historical sets of data. Now, when you have this data, you want to start thinking, what am I trying to solve? What should my model do, right? And then you gather this data and then you start to clean this data. So you can, when you have the idea of what you're trying to do, right? You know what your features are, right? Your features are generally your X variables or independent variables, sometimes called input, right? So you input something and then you want your output, which is your Y. Essentially, you have this set of input and you want to get the set of output, but you need to clean the data and make sure you process it correctly, because data is not usually clean. If you go in a real world, you might get a bunch of data, but they might be in different places. Some might be missing some columns. Some might, you want to clean all that to make sure, okay, my data is good enough to make some predictions. Now, once you've cleaned your data, you probably want to select an appropriate algorithm, right, that you're going to use to train your model. So once you finish that evaluation, right, you get the output from your evaluation, and then you say, oh, is this good or not, right? Is this data good? Sometimes it's not usually perfect at the beginning, right? You need to fine tune things to make them work properly. So if it's not good enough, you send it back, right? Send it back for cleaning and processing. And now you redo the process again, and you redo it how many times you want, right? You keep sending it back until you get the right model that you're looking for. And then you export and deploy that model. Once you deploy that model, you can just use the model and bring in new data, and you'll get your quality data, your results based off of the predictions from the model. So essentially, this is what we deployed to our server or wherever you want to deploy it for use. Let us go back to our problem statement. So in our problem statement, we see that we will be deploying our ML model in this ML API service so that once the sensor value changes, or maybe after a particular time, it calls our ML API service and say, okay, what should my value be, right? What should my settings be? And based off of that, the ML API service can use the model that we've developed and now send that command and say, turn on the fan in Parsons' room, or turn on the fan in Francis's room. And that is exactly what we're going to try to build by the end of this machine learning IoT session. So, in our last video, we had our API service. We had a system where our microcontrollers talked with our MQTT broker, and through our device event hub, right, it was able to send data to our API service, and our API service can communicate to Google Cloud. Also, Google Cloud service, which we had the Google Cloud app or the Google app, right, could communicate using our API service and talk back to our MQTT broker, which then communicates with our device. Now, for this video, we're going to do something a little different, right? So, looks a little simpler, I would say, right? So, we still have our microcontrollers, our ESP32s talking with our MQTT broker. And then we have our events hub taking data from the broker if they want to talk to the API service, right? It takes it and then sends it to the API service. All right. The reason why we're doing that is because the ESP32 is a very small microcontroller. It doesn't really have that much capacity to do a lot, right? We're already using it for a lot of things. We're using it to send data to our MQTT broker. We're using it to connect to Wi-Fi. There's a lot that we're already using it for, right? So just to simplify that, work on it, right? And make it easier on the microcontroller. We have this event hub to pull that data and call an API service. Now, once the API service gets the data, let's say temperature increased to 70 degrees, right? And the time is 3 p.m. on a Saturday. Let's say the API service gets that data. It then communicates with our ML model. It passes that data into the model and says, okay, here are the current sensor and time values in this room. What should our target be? And so the ML model will say the fan should come on, or the fan should be off. I would say if the temperature is really cool, the fan should be off, right? And if maybe we had like 75 degrees or 70 degrees, maybe the fan should come on, right? And then once it makes that prediction, the API service can then send that data to the MQTT broker, which can then relay it back to the device. Now, this is very simple, right? So here are some ML training algorithms that you could use when creating your ML models. We have supervised learning algorithms, which is what we are going to be using for this training, and that usually just involves learning from labeled examples. Now I highlighted these three here, these three algorithms here: linear regression, decision trees, and random forest, because we're going to be, you need a little more understanding on how those work. We also have unsupervised learning, and usually this involves discovering patterns in unlabeled data, and reinforcement learning, which usually means you're learning from trial and error. So there are different types of models. You can read about them and try them out. Now, like I said earlier, like you need understanding with basically these three different models. For this particular training session, this IoT ML session, we used the random forest. However, it's good to have a basic understanding of these two also. So in a linear regression model, it's like a linear representation or a linear mapping of things where 10 o'clock in the night or you assume like my temperature is cool, so switch off the fan, right? Because usually the temperature in the middle of the night is usually cooler. Now that might not be the case all the time. There are some months where the night is usually hot, but it's just an example, right? Decision tree is used like a tree-like model to recursively split data and features to make decisions, right? So for example, if we look at the data and we examine the data and say, okay, is it more than 9 o'clock, right? And then for those that are not more than 9 o'clock, right? So for the data that we see that the time is not more than 9 o'clock, well, we can assume that in the morning, like the temperature, not all mornings, but we can assume that the temperature is usually lower in the morning. So maybe we don't want to put the fan on. And then for those that are more, maybe it's 10 o'clock or 11 o'clock, right? Those are more like higher in the day. We can say, okay, for those data, we can say, okay, we probably want to examine this data a little bit further. Is it more than maybe 6 o'clock? Maybe we can assume that, is it less than 6 o'clock, right? Data that has time that's less than 6 o'clock. And then we can say for those that are more than 6 o'clock, we can assume that by 6 o'clock, the sun is down, right? Not all in all cases, but we could just assume in that case. And then that data, we can say, okay, we don't want to turn on the fan at that point, right? And then for the data that's, more than 9 o'clock, but less than 6 o'clock, we could say, let's look like a good time when we want to turn on our fan, right? So it's just a simple example there on how you could make decisions by splitting data. In random forest is an ensemble of decision trees. So you have different decision trees, and you aggregate those predictions together and use that to make a much more accurate result. Now, let us solve a simple ML problem. So in this problem, we have, okay, let me read the problem. The database, that database contains data for multiple patients. It contains sets of features X and a goal field Y, which refers to the presence of heart disease in a patient. It is an integer valued from 0, which means no presence, to 4. Create an ML model that can predict the presence of heart disease in a patient. Okay, let's open up this URL and get the data. Okay, so where is this URL from? So this is from UC Irvine, right? And it has this data here. So there are a lot of features. We see age, sex, CP, BPS, cholesterol, and a lot of medical features, right? And now we need to use this data. So let's look at, so it says to import in Python, this is how you fetch it. You have to install this UCIML repo, and then you get the data. All right. First things first, let's open Colab. Colab.research.google.com. Okay, create a new notebook, right? So new notebook, right? We talked about the process, right? Where we have historical data, we get our data, we clean our data, then we run it through algorithms and evaluate it and try to use those algorithms to create a model. And then we check if it suits what we want. If not, we will send it back. If it does, fine, right? Then we will deploy, right? So let's create a template that we're going to use to solve this problem. Let me create a text at the top. I'll just create a few text here. So we'll put our problem statement, okay. Now I've finished creating the groups, right? So basically we have our problem, a group for our problem statements, and the libraries we're gonna import. Then we're gonna load the data, right? So we'll get the historical data, that's this point here. Then we're gonna process the data, that's this point here. Then we're gonna train our data, right? That's here. We train our data so that we can get the model. and we'll validate and tune our data. That's at this point here, check and tune. And then here we'll download and deploy our model. Okay, we'll just download. We don't have to deploy it anywhere for this point. All right, so before we import anything anyways, we need to install the library that we need to get that data, right? So let's go ahead and add that. Okay, so we get in the UCIML repo, right? And now once we have that code, let's see if we can install it. Okay, so that's been installed successfully. Okay, so now let's go ahead and do the necessary file import. So let's put in some of the libraries that we're gonna need. And so that's the UCIML repo that we just installed using pip. We'll need a pandas, numpy library. We're just gonna use the pprint just to print, make things clearer when we print. And then we're going to use scikit-learn and use the random forest classifier from scikit-learn. Right, so now these are the libraries that we need. So we can import those libraries. Okay, the libraries have been imported. So now let's get the data. So basically from the library, we're getting the features and the targets, which is the X and Y variables. And we're just printing out what the names of the variables are. Again, you can see the variables that we have for these data sets, like age, sex. I think there is some explanation of some of these figures, like this is cholesterol. There's some explanations for some of these. You can get the explanation. I think there's another. If you read the document, you'll be able to get what those means. Yeah. So now let's process our data. Let me add some code in here. So one of the first things I'd like to do is we like. Basically, you can detect the stages of heart disease from the problem, right? The problem says there's a 0 to 4, but we would like to just detect if there's no heart disease. So anything from 1 to 4 will say that there is heart disease, and anything at 0 will be that there is no heart disease. So here's the data with all the we've dropped all the NaN values, and now we have clean data, right? You can take this out. Okay. So this is the column that has our target, right? Num. And now what we're doing is we're cleaning up, we get that column, right? And then we say like if it's 1 or greater than 1, right? If it's greater than or equal to 1, we just want to make it 1, right? Right, so we just want to make it 1, right? We'll make it 1 if it's greater than or equal to 1. Otherwise, we'll set it to the value that it currently is, right? And here, what we're doing is we're going to take that column out of the table. So if you look at that value, that data again, does it show everything? It might not show. Okay, this just shows if we have missing variables or not. Oh, okay, this is what I was looking for. Okay, yeah, this is what I was trying to explain, the description. So rest BPS means resting blood pressure, seldom cholesterol, fasting blood sugar, FBS. So there's some explanation there, a number of major blood vessels. And then you can see here number 13 is num, right, which is our target. And that means that's the diagnosis of the heart disease, right? And so when we cleaned up the data, you can see num is here, right? Our target is here, but we need to separate our X from our Y, right? So that's what we're doing here, right? So we're getting our Y, we're taking it out of the group, and then we're getting our out of the group and then naming the group that's left over after we take it out X. And before we, after we took out our Y, we're saying that anything 1 or above, just make it 1. So we just say, okay, they do have a heart disease, right? We don't want to know about the level. We just want to know if there's a heart defect or not, right? And so let's test this out, right? So we can create a new code here. We can print out, let's first print out our X column, right? So if we do that, we could see the table, the same table, but without the Y, right? And then if we printed out our Y, right? We'll just see, we just have the num, right? So you can see here what we've done is we've separated the X and the Y columns, right? Next thing we want to do, we want to split our data into training data and test data. Now the training data we will use to train the model, and the test data we will use to test the model after our training is complete, right? So this is still under processing, right? So we would add some code for that. And here we are splitting our data, right? So let's run this, make sure it works, okay? So now we have X train, X test, Y train, and Y test. We're gonna add some code for training. And initially what we're doing is we're using a random forest classifier, right? So basically we're initializing the OOB score. Usually this is good because it gives us an estimate of how our model does. It's just a score to see how good our model is, right? And we're using a maximum depth of 4 and a random state 90, and then we're fitting our model in order to train it, right? And let's run that. Now that we've trained our data, you can see it's about 83%, okay, based on our OOB score. So now let's calculate the accuracy. And now we can calculate our accuracy. It's about 81.6. Like, we can try to tweak some of these things. Let's see. If we increase the maximum depth to 6, will that improve? We had 83, now it's 81. Let's make it 10, and that gonna help us. It's 80, huh? Okay, let's do 4. 4 gives us 83. 3 is kind of small. There are other features that this random forest classifier has. So now we could maybe try assigning weights to some of this, and maybe it might give us a different score. Or you could try that on your own. All right, so we've calculated our accuracy, right? And now let's print our confusion matrix so we can see how well, we can visualize how well this model performed. And so this is the code here for the confusion matrix. And when we run this, let's see what we have. So here's our confusion matrix. Of all the models we had, 28 28 of them we predicted that they didn't have. 28 people we predicted that they didn't have heart disease, and they actually didn't have heart disease, right? That is our false positives, right? So what we predicted, and it worked, right? It's correct. Now, in this code here, like you can see, we're testing this prediction on our test models, right? So, on our test data, rather. So 21 of the people, of the patients, we predicted that they did have heart disease, and they actually did have heart disease. Now there's like a 5% that our prediction was wrong. We predicted that they did have heart disease, but they didn't have heart disease. And for 6 of the people, we predicted that they did not have heart disease, but they actually did have heart disease. So you can see the percentage here. I guess it's not a perfect model per se, but it's just an example that you could use to just learn how things are done. Now that we have our confusion matrix, and we've gone over what it really means. Let's see if we can download our model, and let's run that. So now you can see we have our heart disease model downloaded, and we can use that heart disease model for our prediction. This is just a simple solution, right? Very simple. Now there may be better algorithms you can use for creating models, but we just wanted to show how to just do a quick test on how to generate a model and how to use the model, right? So in the next example, we will be showing how to solve our main problem statement for our IoT problem, but essentially you could see we're just gonna follow the same steps that we have here, right? So, and we're gonna use the same steps to solve these problems, right? Again, I really hope you enjoyed this tutorial, and I know it's a lot. It's a long time watching all of this, but do feel free to subscribe, like, comment, and share these videos, and I will see you in the next one. Thank you.